Hello my friends and welcome back to the You Can Do TV channel. The Hejre oil and gas field, located in the Danish sector of the North Sea, represents a significant development in the region's energy landscape. The installation process of this field is a testament to the intricate planning, engineering prowess, and collaborative efforts of multiple stakeholders. The journey began when the Hejre jacket, a colossal 8,400-ton steel structure designed to support the Hejre platform, was loaded onto the barge H627 in Vlissingen, Netherlands. This jacket would serve as the foundational structure for the platform, ensuring its stability amidst the challenging conditions of the North Sea. As preparations were underway, the semi-submersible crane vessel SSCV Hermod was mobilized from the port of Rotterdam. This vessel, equipped with advanced crane capabilities, would play a pivotal role in the installation process. Upon reaching the Hejre site, the Hermod faced its first challenge, deploying anchors in rough weather conditions. Despite the turbulent seas, the forecast was promising, and the team pressed on. In a coordinated maneuver, the barge carrying the Hejre jacket rendezvoused with the Hermod at the Hejre field. The Hejre field, located in the North Sea, was first unveiled to the energy industry in 2001 with the drilling of the Hejre-1 well. This exploratory well was drilled using the ENSCO 101 jackup rig, reaching an impressive depth of 5,265 meters. This initial drilling endeavor was pivotal in identifying the potential of the Hejre field. With precision, the sea fastening was cut, and simultaneously, the barge was trimmed with ballast to ensure stability. A few years later, in 2005, further exploration was conducted with the drilling of the Hejre-2 well. Once again, the ENSCO 101 jackup rig was employed, this time reaching an even greater depth of 5,399 meters. The results from this drilling activity were promising, as they not only confirmed the presence of oil but also showcased the field's potential. The culmination of these efforts was the launch of the jacket into the North Sea on a Friday evening. This process, which took less than a minute, saw the barge's ballast tanks filled with water, causing a slight tilt and allowing the massive steel structure to slide gracefully into the sea. Ingeniously designed floating tanks and compartments within the jacket ensured it remained buoyant. Following the launch, the next phase was the upending operation. Ballast hoses were connected, and water was methodically let into individual compartments in a predefined sequence. This controlled process slowly brought the jacket to a vertical position. With the jacket upright, the Hermod's crane took over, meticulously positioning the jacket to its exact offset location on the seabed. The culmination of these efforts was the touchdown, marking a significant milestone in the installation process. Hywind Scotland, the world's first floating wind farm. In the vast expanse off the coast of Scotland, a revolutionary idea has come to life. 16 years after its conception on a simple napkin, the world now witnesses the Hywind Scotland, the world's first floating wind farm. This monumental achievement stands as a testament to human ingenuity and the relentless pursuit of sustainable energy solutions. The journey began with a demo version built off the Norwegian west coast, aimed at proving the concept of floating wind turbines. Despite skepticism, the demo exceeded expectations, producing valuable data that further refined the Hywind concept. This innovation is a perfect amalgamation of long-standing offshore operational expertise and the need to harness wind energy in deeper waters. Hywind Scotland is more than just a proof of concept. It's a functional wind farm, with 5 massive turbines that, when looked at from the shore, seem to touch the horizon. Invisible to the eye, a network of cables connects these turbines, transmitting the generated electricity back to the mainland. This colossal project can power up to 20,000 UK homes. The turbines are anchored to the seabed using massive suction anchors, each weighing approximately 111 tons. These anchors, along with the turbines, were a collaborative effort between Scottish and Norwegian companies, showcasing international cooperation in the realm of sustainable energy. The floating substructure, the heart of the Hywind design, distinguishes it from traditional bottom-fixed turbines. With a length of over 90 meters and weighing approximately 3,500 tons, these substructures were meticulously crafted by Navantia in Spain. The turbines themselves underwent an evolution, growing from 2.3 to 6 megawatts since the initial demo. A significant innovation within the Hywind concept is the motion controller. This ingenious system pitches the blades to stabilize the floating structure, optimizing power production even in challenging conditions. However, the journey wasn't without its challenges. From managing multiple contracts to executing heavy lift operations, the project demanded precision and collaboration. One of the most daunting tasks was lifting the fully assembled turbine onto the floating substructure. By August, all 5 turbines were operational at Buchan Deep off Peterhead. This pilot project not only pushes the boundaries of offshore wind technology but also paves the way for larger ventures in new areas. Impressively, the cost per megawatt for the Hywind Scotland project has been reduced by 60% compared to the initial demo. In the realm of offshore projects, the transportation of massive components is a critical and challenging task. The sheer size and weight of these components, such as the 590T offshore tripod or the 212T upright tower segment, demand specialized equipment that can handle their magnitude while ensuring safety and efficiency. Enter the self-propelled modular transporter, SPMT, a game-changer in the world of heavy lifting and transportation. SPMTs are multi-axle platforms equipped with a large array of wheels. These platforms can be combined in various configurations, allowing them to carry exceptionally heavy loads. Their design is inherently modular, meaning multiple SPMTs can be linked together, both side by side and end to end, to form larger platforms. This modularity is essential when dealing with oversized offshore components, as it provides the flexibility to tailor the transporter's size and shape to the specific needs of each load. One of the most notable features of SPMTs is their ability to distribute the weight of the load across their axles evenly. This weight distribution is crucial when transporting massive components like the 590T offshore tripod. By ensuring that the weight is spread out, SPMTs reduce the risk of structural damage to roads or other infrastructure and ensure the stability of the load during transit. The 212T upright tower segment, another colossal component in offshore projects, also benefits from the precision and control offered by SPMTs. These transporters are equipped with advanced hydraulic systems that allow for precise height adjustments. This feature is invaluable when dealing with tall, upright components, as it ensures that they remain stable and upright throughout the transportation process. Furthermore, SPMTs come with computer-controlled steering. This feature allows for synchronized movement of the wheels, ensuring that the transporter can navigate tight spaces, make sharp turns, and even move sideways if necessary. Such maneuverability is essential in the complex environments of ports, shipyards, or construction sites where space is often limited and precision is paramount. In addition to their technical capabilities, SPMTs also play a pivotal role in project timelines. Their efficiency and reliability mean that giant-sized components can be transported faster and more safely, reducing project delays and associated costs. The offshore energy sector has witnessed numerous engineering marvels over the decades, but few stand out as prominently as the Valemon jacket constructed by Hejre Fabrication Group for Statoil. This colossal structure, weighing in at a staggering 9,150 tons, is not just a testament to Hejre Vlissingen's capabilities but also underscores the advancements in offshore engineering and the potential of the North Sea. The North Sea, with its vast reserves and challenging conditions, has been a hub for offshore innovations. The Valemon field, located between the Kveitbjorn and Gullfaks South fields, is one such reservoir that required a robust and advanced infrastructure to tap into its potential. Enter Hejre Fabrication Group, a renowned name in the offshore construction sector, tasked with building the largest jacket ever in its Vlissingen yard for Statoil's Valemon field. Design and initial phases. The journey of the Valemon jacket began with meticulous planning and design. Given the North Sea's challenging conditions, the jacket had to be robust, durable, and efficient. The initial phase saw the first steel cutting at Hejre Vlissingen, marking the project's commencement. This foundational step is crucial as it sets the tone for the entire construction, ensuring precision and quality right from the outset. Construction milestones. The construction process was marked by several significant milestones. Roll-ups. The roll-up process, which involves curving or bending large steel plates to form the jacket's cylindrical sections, was executed in multiple phases. The top part, row 1, was the first to undergo this, followed by the bottom part and then the top part of row 5. These roll-ups ensured the jacket's vertical assembly, providing the necessary height and structural integrity. J-tubes and risers. Essential for the transportation of oil and gas, J-tubes and risers were fabricated with precision. These components guide and protect the flow lines and umbilicals from the seabed to the platform's topside. Cross bracing. To provide additional lateral support and stability against the dynamic forces of the sea, the cross of row A was installed. This bracing ensures that the jacket remains steadfast even in the harshest conditions. Wellhead module. The heart of any offshore platform, the wellhead module, controls the extraction process. This 210 metric ton module, designed by HFG Engineering and constructed by Hejre of Vlissingen, ensures safe and efficient production. Load out and transportation. With the jacket and its components ready, the next challenge was its transportation to the North Sea. The load-out operation, a significant logistical feat, involved loading the massive structure onto a barge. Given the jacket's size and weight, this operation required state-of-the-art equipment, precision, and coordination. The sail away to its offshore destination marked the culmination of months of hard work. Navigating through open waters with such a colossal structure demanded detailed planning, expert navigation skills, and a thorough understanding of the North Sea's conditions. Installation and operations. Upon reaching its destination, the Valemon jacket was anchored to the seabed, providing a stable foundation for the Valemon platform. The installation process, carried out in a water depth of around 135 meters, was a significant engineering challenge. The jacket serves as a foundation for the Valemon platform, equipped to treat gas and condensate from nearby discoveries. The platform's operations are a testament to the jacket's robust design and construction, ensuring efficient extraction and transportation of resources. The Valemon oil and gas field, situated in the North Sea, stands as a testament to advanced offshore engineering and the potential of the region's hydrocarbon reserves. Located between the Kveitbjorn and Gullfaks South fields, approximately 160 kilometers west of Bergen, the field has been a significant contributor to the energy sector since its discovery. Discovery and development. Valemon was discovered in 1985 and has since been a focal point for energy extraction in the North Sea. Production commenced on the 3rd of January 2015, marking a significant milestone in its development journey. The field development consists of a remote-operated, fixed jacket platform equipped with a streamlined separation facility for gas, condensate, and water. This advanced platform is designed for remote control from an operations center located at Sandsli in Bergen, showcasing the integration of technology in modern offshore operations. Reservoir complexity. The Valemon Reservoir is situated at a depth of around 4,000 meters and is known for its complexity. The reservoir is not only fractured but also characterized by high pressure and high temperatures. Despite these challenges, the field has been a significant contributor to the energy sector. However, the recoverable volumes have been revised over time, with the 2021 plan estimating a recovery of around 18 billion cubic meters of gas, 0.2 million cubic meters of NGL, and 2.3 million cubic meters of condensate. Transportation and infrastructure. The extracted condensate from Valemon is transported via pipeline to the Kveitbjorn platform for stabilization. Post-stabilization, it is further transported to the Mongstad refinery located in Hordaland. The gas from Valemon has a two-phase transportation plan. Until 2023, the gas is directed to Heimdal. Post-2023, the gas will be co-transported with the condensate for separation at Hyperbaric. Subsequently, the gas is processed at Kollsnes, north of Bergen, before being routed to the European gas markets. An added feature of the Valemon field is its electricity supply, which is sourced from Hyperbaric through a submarine cable. Recent discoveries. In a significant development, Statoil announced a new gas discovery near the Valemon field, named Valemon West, 2 years after Valemon commenced its operations. This discovery is estimated to contain between 20 and 50 million barrels of oil equivalent. Gunnar Nacken, Statoil's senior vice president for the Operations West cluster, emphasized the importance of this discovery for the further development of Valemon. He highlighted the opportunities that still exist in the North Sea and the potential value these reserves can bring. Veja offshore wind farm installation. The Veja offshore wind farm stands as a testament to the marvels of modern engineering and the potential of renewable energy. Located approximately 130 kilometers north of Eemshaven in the German section of the North Sea, this wind farm boasts a capacity of 400 megawatts, enough to power 400,000 homes in Germany. The wind farm is situated about 95 kilometers NW from Borkum Island in the German exclusive economic zone, an area renowned for its strong and consistent winds. With water depths ranging from 39 to 41 meters, the installation of the wind farm presented unique challenges. The project's scope encompassed the design, procurement, manufacture, transport, and installation of the foundations for 67 wind turbines. These foundations consisted of enormous monopiles and transition pieces. The monopiles, designed and fabricated in Rostock, Germany, are truly colossal. They are the world's largest, with a staggering length of up to 85 meters, a diameter of 7.8 meters, and weighing up to 1,300 tons. The transition pieces, each weighing 350 tons, were fabricated in Aalborg, Denmark. Both components were then transported to a marshalling yard at Eemshaven, Netherlands, in preparation for installation. The installation process was spearheaded by the Sea-Jack Skyla, a new generation jack-up installation vessel equipped with a crane capable of handling 1,500 tons. This vessel was responsible for installing the monopiles, while the Sea-Jack Zaratan transported and installed the transition pieces. The installation strategy involved transporting 3 monopiles at a time on the Skyla and 6 transition pieces at a time on the Zaratan, ensuring the project proceeded in sequence. A significant aspect of the installation was the scour protection, executed using Boskalis' fall-pipe vessel, the Rockpiper. This process was initiated after a thorough unexploded ordnance detection and removal across the site. Noise mitigation was another crucial component of the project, given the strict underwater noise requirements in Germany. To meet these requirements, Boskalis employed a hydro sound damper on the gripper frame and a double bubble curtain, ensuring that the noise levels remained within the agreed limits. The Veja project was completed in the fall of 2016, with the wind farm expected to be fully operational by the end of 2017. This endeavor showcases the expertise in EPCI project management and the installation of offshore wind turbine foundations. The success of the Veja Mate project is a testament to the dedication, innovation, and resilience of all the teams involved, paving the way for future offshore wind energy projects. In this part, we will learn about the Nord Stream gas pipeline installation project. The Nord Stream project is installing two 48-inch gas export pipelines from Vyborg in Russia to Greifswald in Germany, through the Gulf of Finland and the Baltic Sea. The two 1,224-kilometer offshore pipelines are the most direct connection between the vast gas reserves in Russia and energy markets in the European Union. Combined, the twin pipelines have the capacity to transport a combined total of 55 billion cubic meters (BCM) of gas a year to businesses and households in the EU for at least 50 years. As the project strengthens the EU energy market and reinforces security of supply, the project has been designated as being of European interest by the European Parliament and Council. Each of the two Nord Stream pipelines is constructed in 3 sections. Once completed, the sections has been welded together to form the 1,224 kilometers pipelines. This tie-in process has taken place on the seabed in an underwater welding habitat. Welding operations were remotely controlled from the Scandi Arctic dive support vessel, and divers has assist in monitoring the subsea construction work. This is pipe handling frame, PHF. The PHFs move the pipeline ends into tie-in position. They can lift up to 150 tons. Lift bags are installed on the segments and filled with air. Once filled, the bags can lift up to 20 tons, helping the PHFs to manipulate the extremely heavy pipeline segments. PHFs not only lift the pipeline sections, they also shift them sideways to line them up for welding. This is tie-in equipment. The welding habitat supplied by Statoil PRS is a dry zone where divers work without diving equipment to set up the automatic welding machine. The welding is completely controlled from the dive support vessel. The state-owned PGN, Perusahaan Gas Negara, supplies over 80 million customers with gas in Indonesia. One of their major offshore pipelines, transporting gas to Jakarta, showed signs of leakage during an inspection in 2013, and it was temporarily fixed with a clamp. DCN International Diving and Marine Contractors and its Indonesian partner SGI were aware to contract to seal the tear in the 4-year-old pipeline by PGN. PGN decided to carry out a permanent repair to the 32-in, 81 cm pipeline at a depth of 27 meters, 89 feet, while the pipeline remains fully pressurized. "15 divers will be specially trained for the PGN project here at DCN in Bergen op Zoom, of whom 10 pre-qualified divers will eventually be deployed of this team. 9 divers will be spending approximately 1 month in saturation, in order to carry out the repair according to the welding method DCN proposes." This is a challenging project because the repair had to be completed without shutting the pipeline down. Contractors developed a methodology to stop the leakage of the temporary pipeline repair clamp in place. Based on extensive analysis on bending moments at the intersection, a permanent repair by means of a welded structural sleeve was performed, ensuring the long-term integrity of the remainder of the pipeline's lifetime. To be able to meet this project, DCN proposed carrying out the welding work underwater, in dry conditions, through the use of what is known as a habitat. A habitat is a sealed working space that offers divers a safe and protected working environment while on the seabed. During the summer, here in Bergen op Zoom, DCN carried out a series of dry runs and tests. DCN endlessly simulated all the elementary welding tasks necessary to ensure the long-term success of the repair at their own location.
You're going to find it in Indonesia.
The tests were in fact carried out by the same divers who would eventually be required to carry out the work at a depth of 27 meters in the Java Sea, under considerable pressure. After the extensive testing program, all the risks had been identified, minimized, and managed. The containers of equipment were shipped to Singapore, including the complete saturation diving system and the habitat with suction anchors, piles. The Normand Baltic, the DP2 diving vessel, was chartered for the project, equipped with a 100 metric ton crane, moon pool, and helicopter deck. The 5-6 meter long piles was installed in the seabed made up of silt and clay. The first pile was used as a trial, in order to determine the required suction force, and to calculate the theoretical load-bearing capacity. The habitat subsequently had to be placed on the remaining 4 piles. Following the hermetic sealing and purging of the habitat to lower the water level, the first gas containment barrier, a sort of safety clamp, was mounted on the pipeline, followed by the lower and upper sleeve. The divers were then able to start on the demanding welding process while the gas continued to be pumped through the pipeline.
Oubliez la gaffe.
Je regarde les mecs ce qui se passe.
Over a period of 10 days, welding was carried out uninterrupted, while the welded layers underwent continuous ultrasonic testing. Finally, the repaired section of the pipeline was fitted with an anti-corrosion wrapping. Four decades ago, the Brent field platforms stood as symbols of industrial might and energy prowess. These platforms, located in the North Sea, played a pivotal role in powering Europe's homes and businesses. But as time passed, the inevitable question arose: how would these massive structures be decommissioned? The Brent field platforms, after years of dedicated service, were slated for decommissioning. The challenge was immense. These platforms were not designed to be lifted in the manner required for their removal. In 2017, Shell astounded the world by lifting the Brent Delta platform intact and transporting it for recycling. This set the stage for Brent Bravo's turn. The task was not just about repeating the process but improving upon it. The goal was clear: lift the 25,000-ton topside of Brent Bravo from its base in the North Sea and transport it safely for recycling. This was no small feat, especially considering the platform's design and the unpredictable nature of the sea. Shell's approach was innovative. Instead of attempting on-site dismantling, the decision was to remove the entire upper platform, or the topsides, as one unit. This involved isolating the reservoir, ensuring no hydrocarbons could escape, evacuating personnel, and then preparing for the lift. The process was streamlined, with lessons from the Delta lift leading to a 70% reduction in preparation work for Bravo. A significant challenge was how to cut the Bravo free from its 150-meter high base without using the steel bracing that was employed for Delta. The solution? Shear keys. These were inserted into the concrete walls of the platform's legs, providing both strength and stability. Once in place, a diamond wire cutter sliced through the concrete wall, ensuring the platform was ready for lifting. The world watched as the pioneering Spirit, the world's largest construction vessel, approached Brent Field. This ship, with its unique twin-hull design, was integral to Shell's single-lift concept. The vessel's advanced technology allowed it to connect its lifting arms to Bravo with pinpoint accuracy, ensuring no contact with the platform's legs. And then, in a breathtaking moment, 25,000 tons were lifted in just 9 seconds. The success of the operation was a testament to the meticulous planning, coordination, and engineering prowess of the team involved. But the journey wasn't over. The pioneering Spirit transported Bravo towards Hartlepool, where another marvel of engineering, the Iron Lady barge, awaited. The topside was transferred to this barge, which was then towed to the Able facility for recycling. Shell's commitment to doing things right was evident. Their partnership with Able promised a recycling rate of 98%. The Brent Field, which had been a part of oil and gas history for 40 years, was now setting a new standard in environmental responsibility. The Prelude FLNG, after traveling almost 6,000 km, has reached Australia. Its mission? To produce liquefied natural gas for a quarter century. But before that, the mammoth task of mooring the world's largest floating facility awaits. Situated 200 kilometers off northwestern Australia, a dedicated rigging crew begins the process. Their goal for the day is to secure the 8th mooring leg. This isn't just another day at work. The Prelude, when fully loaded, weighs a staggering 660,000 tons. 6 times heavier than the world's largest aircraft carriers. Given its location in a region notorious for extreme weather, the mooring system's reliability is paramount. It's designed to withstand cyclones, keeping the facility anchored securely. The mooring system's heart is the turret inside Prelude, enabling it to rotate. Beneath it lies one of the world's largest chains, with almost 25,000 links, anchored deep into the ocean floor. The team is now set to connect the 8th chain, ensuring Prelude's safety against storms. The process is intricate. The rigging team descends into the turret's depths, while tugs maintain Prelude's position. The Deep Orient crew retrieves the mooring line, and a colossal winch on Prelude stands ready. As the chain is hauled in, engineers monitor every move. The culmination of years of planning is in action. The chain's emergence is a sight to behold. A specific link indicates the correct chain length, ensuring the facility's anchoring to the seabed. Once the 8th mooring line is connected, Prelude achieves its storm-safe status. This is just one of the 16 mooring lines that will keep Prelude anchored for the next 25 years. A historic moment, indeed. The Aasta Hansteen Spar is a marvel of modern engineering, representing a significant milestone in offshore natural gas extraction. Located 186 miles offshore in the Norwegian Sea, it is operated by Equinor and stands as the first spar platform on the Norwegian continental shelf, NCS. The platform is named after Aasta Hansteen, a renowned Norwegian painter, writer, and early feminist. Design features. The Aasta Hansteen platform is a truss spar type, which allows condensate storage in the hull below sea level. This condensate can then be offloaded to a shuttle tanker. The gas produced is exported to the shore using steel catenary risers, SCR, marking the first time SCRs have been utilized in the Norwegian Sea. The platform's design is a collaborative effort, with the spar hull designed by Technip and the topsides by CB&I. Both components were fabricated by Hyundai Heavy Industries in South Korea before being transported to Norway for installation. The spar hull, with a height of 198 meters, 177 meters submerged, and a diameter of 50 meters, is the largest of its kind in terms of diameter and displacement. The platform exports natural gas through the Polarld pipeline to the Nyhamna processing plant on the Norwegian coast, with the entire project costing approximately 37.5 billion Norwegian kroner. Transport and installation. The construction process of the Aasta Hansteen Spar was unique. Built on its side in dry dock on barges, it was floated off and then transported on the heavy ship Dockwise Vanguard to a fjord near Stord in western Norway. In the fjord, the spar was upended, and the topsides were installed using the float-over technique. The platform was then towed vertically to the Aasta Hansteen gas field, 300 kilometers off Bodø on the northwest coast of Norway. It is moored north of the Arctic Circle using polyester moorings anchored to the seabed 1,200 meters below. Production began on the 17th of December 2018. Aasta Hansteen gas field, originally known as the Lova gas field and renamed after Aasta Hansteen. The field was discovered in 1997, approximately 300 kilometers off Norway's coast. As the platform started up, gas from the surrounding Lova, Haklang, and Snefrid fields was exported to it. There are plans for future fields already discovered to be tied back to the Aasta Hansteen platform through SCRs. The platform's design also accommodates the future expansion of additional risers and topside facilities. Positioned north of the Arctic Circle, the field faces perpetual darkness and sub-zero temperatures during winter. The Suez Canal, one of humanity's most monumental achievements, serves as a vital maritime passage for over 17,000 ships annually. However, a significant limitation existed. A 35-kilometer stretch allowed only one-way traffic, causing vessels to wait up to 11 hours for ships from the opposite direction. This inefficiency prompted a 21st-century upgrade, a new parallel canal to facilitate two-way traffic. Originally, experts estimated a 3-year completion time. However, the Egyptian president ambitiously aimed to inaugurate the new canal within a year. This set in motion an unprecedented operation. With minimal preparation, the project was handed to a consortium, setting a daunting target: complete the canal in just 10 months. Equipment from across the globe, including Europe, Asia, and South America, converged on the site. The result? A 35-kilometer canal, 24 meters deep and 400 meters wide, carved straight through the desert. The project's scale was staggering. In total, 200 million cubic meters of sand were excavated, equivalent to relocating 80 Great Pyramids of Giza. At its peak, production reached 65,000 cubic meters a day. The project's nerve center, located in Ismailia, oversaw the logistics and equipment, with 28 units, the largest number of dredges ever used on a single project. With nearly 1,800 personnel on site and 23 dredges operating simultaneously, coordination was paramount. The team worked tirelessly, ensuring any issues were swiftly addressed, with operations running 24/7.